Hi, and welcome to our third example of internal resistance. Let's look at our diagram here. They've given us in this circuit two identical cells. These are two cells, okay, with an EMF of 1.6 volts. So both of them can provide an EMF of 1.6. Oh, that's the resistance. The EMF is 1.6 and 1.6, so it has a total EMF we can therefore see of 3.2 volts would be the total one, the total possible voltage that it could supply. And it also has, both of them have internal resistance R. Okay, and they are connected in series, which is an important fact because in series we add up the voltage that they supply, and they are connected with each other, and the resistors are as shown below. So these two resistors are in parallel. Okay, they give us the two resistors. This is a 4 ohm resistor and a 5 ohm resistor. Excellent. Define in words the term electromotive force. Now there's two ways to define electromotive force. The first one, you can say it is the total potential difference measured of at the two electrodes of a cell. That's the one way you can define it as, or you can define it as the sum of voltages across external resistances and the internal resistance. Okay, so that's defining EMF in words. Write down the total EMF of the circuit. Well, we calculated it. Since they are in series, we just add it together like that. So 1.6 volts. If they were in parallel, how would we have done it? Okay, in parallel, remember what voltage is. Voltage is the joules per coulomb. So if this battery gives my each coulomb 1.6 joules, and this one gives it 1.6 ones as well, then the total that is given is sorry, I shouldn't do it like this. Okay, there we go. So let's say my batteries were like this. For this one, the total, the one as the coulombs come in, they get 1.6, and they go into the next one, they get another 1.6. So they have a total of 3.2 volts received. Here, each coulomb comes out here with 1.6 volts. Each coulomb comes out here with 1.6 volts. It only goes into one charging center. Let's call a cell a charging center. Okay, it doesn't go into both of them. So not unless they are like you see often in toys, and when you put batteries in there, they're like this. Now this looks like they're in series, in parallel, but they're not. They're actually connected like this. Okay, which makes them in series. Nevertheless, let's go on. It's 1.6 plus 1.6 volts is equal to 3.2 volts. That's the total in the circuit. When the switch is closed, the potential difference across R1 resistor is 1.2 volts. Okay, so they're saying when we closed the switch, this R2, the potential difference across the R1 resistor. Okay, suppose that one. Yeah, I don't know why they let's fix it. Let's make it the R2 resistor is 1.2 1.42 volts. And so 1.42 volts, since this is where the potential difference is measured, and then they ask us the following: calculate the total current in the circuit. Okay, total current in the circuit. Now let's quickly go and follow the current. As the current passes from positive to negative, it passes out here. Okay, it comes, this is the total current that comes out here, but here the current splits into two. Okay, so if we calculate the current that passes into R2, it's not the total current. Now we've got enough information to find the current in R2, okay, because we've got resistance, so we can find I2. I2 is just V2 over R2. We've got all of that information, but the current had split up. So in order to find the total current, we'll also have to find the current in 1. So either we can do that, and if we wanted to do that, we'll have to say we need the voltage over R1 divided by the resistance in R1. Now here is the important fact, something that we always have to remember when we work with circuits, that voltage is the joules per coulomb that each coulomb have. So the joules that each coulomb have, I mean. So if I have 1.42, that means that when it comes here, it's going to spend 1.42 volts at this resistor. Now the same goes for this one. This one, even though it's a different current, the amount of energy that it will spend in the two branches must be equal. Okay, so this one will also have a 1.42 volts reading if we were measuring it over here. Very, very important that you know that. Okay, so we do have both of these values. Since we have all of these values, we can just add them together so to get the total current. Alternative approach would be that since I have to divide to determine the total current, I can just take the voltage over the load divided by the load itself. Okay, so if I say voltage over the load, it means the total external resistance divided by the voltage over the total external resistance divided by the total external resistance. Now the voltage over the total external resistance, again, what is the difference between the energy that a coulomb has at this point and that it has at that point? Well, the energy that it has at this point gets spent at R1, 1.42. So after that, it has 1.42 less. The potential difference for a coulomb that goes this side, exactly the same. So here is again the important fact: the voltage over one branch in a parallel construction is equal to the voltage over another branch in a parallel construction is equal to the voltage over the whole parallel construction. Very important. So I've got all of this. I've got the voltage load. I can get the external load. It's just two resistors in parallel, and then I can get the resistance of the external load. So whichever one you want to choose, I'm going to go for I1 and I2. Okay, so let's do it here. So I2 is resistor 2 is the voltage 1.42 divided by the resistance of 2 is 5, and that would be equal to 0.284 amperes. I1 is the same voltage, 1.42 divided by 4, and that is 0.23, 2 left, 22, 4 goes into there 5 times, 2 remains, and it goes into there a half times. Okay, I think so. No, I lie. Like that. Okay, there we go. These are the currents in each of the branches. So total current is just the sum of these two. So that's a 9, that is a 1360,639 ampere. That's my total current. Excellent, that's not too difficult. Okay, so 0.639 ampere. Look at the amount of marks I'm going to get for answering that simple question. Calculate the internal resistance of each cell. Great stuff, because I've got this wonderful formula that we looked at before. We looked before that the EMF is equal to the total current times the sum or the total resistance, which is the resistance, the load plus internal resistance. Okay, now if I multiply this in internal resistance times R, because I don't have R, okay, I didn't calculate it. If I used this approach in my previous question, this one, I would have had to go and calculate R, and then I could have used this formula. So what I'm going to do is I'm just going to multiply in, and you'll see now in just a second why I did that. It shouldn't be such a small R, okay? Because I have the EMF. Now, total current times resistance is just the total, the voltage of the load, and I have the voltage of the load. The load is all the external resistance, and I have the voltage over the external resistance. That's 1.42, and now I have the current, the external current, and I want to calculate resistance, so I'll keep this as it is. So my EMF is 3.2. My voltage over the load is 1.42, plus my current is 0.639, and then my resistance is what I want to calculate. So all I need to do now is simplify. So R is equal to 3.2 minus the 1.42. I'm just solving an equation, divided by what's in front here, 0.639. What answer do I get? So I get 3.2 minus 1.42 divided by 0.639 is equal to 2.73 is equal to 2.856. So let's keep it 856 for now. 7856. This is the internal resistance of the battery. Okay, the total internal resistance. But remember, they're asking us for each cell, so we have to keep in mind that this would be the resistance, since these two resistors are in series. Very important, these resistors are in series with one another, which means we added them together. And so to get the resistance of each, I just need to, so for each, I'll just divide it by 2, which will give me 1.3 to get 73,928. So if I, and this was supposed to be an ohm, so if I just round that, that's about 1.39 ohm. Excellent, that's a wonderful answer. Thank you very much. Let's go on to the next question. An unknown resistor is now connected in parallel with R1 and R2. How will this change or affect the magnitude of, okay, so let's go and see. If we added another resistor in here, let's change color so you can see what I'm doing. If I added another resistor in here, how will this resistor affect, first of all, the internal resistance? Well, the internal resistance of a battery is the internal resistance of a battery. Adding anything to the outside circuit doesn't change the size of the internal resistance, and that still remains a constant. Okay, so if we look at internal resistance R, that's a constant, so changing anything on the outside of the circuit doesn't change that value. Okay, however, now it asks us this question. This is a very interesting question. How does it change the reading on the voltmeter? How does it change the reading on this voltmeter here? Now let's go and look at our formula again. That reading on the voltmeter is E is equal to my total current, no, the voltage of the load plus the volts lost. Okay, now the voltage on the load, that is what we want to calculate. Voltage on the load. What will happen to it? Voltage on load. That will be equal to my EMF minus the volts lost. And now, how many volts do we lose? Well, does that change at all? Let's look. EMF is a constant. Okay, it doesn't change. It's a constant. But the volts lost might change, because volts lost depends on the total current times, so I'm just doing this, okay, volts lost is not constant. Volts lost depends on the current. The stronger the current, the more volts I will lose, because voltage is current times resistance. So volts lost is the current times the resistance in the battery. So the bigger the current, the more resistance will be lost in the current. Okay, or in the battery, I mean. So the question is going to be, if the current increases, then I will lose more volts, which means the load will have a lower reading. Does that make sense? I think it does. Okay, if the current decreases, I will lose less volts, and so EMF is constant. I will lose less volts than I lost before, and so my load will increase. Okay, so let's go and look. That's what we need to find out in the end. Is the current going to increase or decrease? Well, again, remember, parallel has this strange effect that when I add another branch, what I'm actually adding is another option for the coulombs to go in. So where I only had 2 directions to go in, now I've got 3 directions to go in, which means I've got less resistance in total. Like if I only if I had a door, if we were at in a big building and there were only 2 doors open, okay, the amount of people that can pass through per second is less than when I open another door. Even if that door is smaller than the other doors, in other words, there's more resistance in this door, it is at least another door that's open. So the moment I add a branch, I am decreasing the resistance, the equivalent resistance. I don't know, for me it now makes intuitive sense. But you can also go and look at when we calculate RT like this. Okay, this is a fraction, and if I add it, if I increase the right hand side of this fraction, this side, if I increase the right hand side, I will increase the fraction. But in the end, I'm going to flip the fraction around, and the bigger the thing is that I flip around, the smaller the flipped around answer will be. I don't know, go and watch the videos on parallel if you didn't get that. Anyway, so my equivalent resistance, my external resistance will decrease. Okay, so if external, so total resistance is equal to total volts divided by total resistance. So if I say if I rather do it like this, total current is equal to the load divided by